Geology at, okay, let's try again. Lori Dengler is Emeritus Professor of Geology at Cal Poly Humboldt, formerly HSU, and she's an expert in earthquake and tsunami hazards and hazard mitigation. Since retiring from teaching, she continues to provide scientific advice to the Redwood Coast Tsunami Work Group, engage in earthquake and tsunami outreach projects with California Office of Emergency Services, and writes the Not My Fault column that appears in the Eureka Times Standard most Sundays, which are a lot of fun, by the way. If you should read it if you haven't had a chance to do so. They're wonderful. She received her bachelor's, master's, and PhD degrees in geophysics from the University of California at Berkeley and taught at the HSU Geology Department from 1978 to 2015. She was a member of the team that developed the U.S. National Tsunami Hazards Program and has participated in 6 international post-tsunami survey teams. Maybe 7 by now, for all I know. I'll have to ask her. She can say it. She was recognized as HSU Scholar of the Year in 2008, received California's Alquist Medal for earthquake mitigation efforts in 2009, and was recognized with the Frank Press Award from the Seismological Society of America for public service in 2017. She should have earned another one by now. In 2015, she published a children's book about a tsunami debris boat that connected cities in Japan and California, and has developed a K-12 curriculum based on the tsunami boat. You can visit and see that. Anyway, I'm delighted to invite her back again, and it's all yours, Lori.
Okay, now we get to see if I can do the hardest part here. Great. Okay, are we good?
We're good.
All right.
Thank you.
Thank you. Thank you so much for having me back. Today's talk is going to be a little bit out of my usual bailiwick. And a caveat, I don't consider myself to be a volcanologist or an expert on volcanic processes. But fortunately, I've spent most of my career surrounded by people who know more than I do. So today we will be focusing on Iceland, and this talk is a combination introduction to volcanic processes and learning to live with one's hazards, and a remembering of a wonderful summer vacation in 2023 when my husband and I spent 17 days in Iceland. So this is a really extraordinary place, and we'll be talking about ridges, rifts, hotspots, and also how this very small country, both in terms of land mass and population, has really made some extraordinary contributions. I will be returning to these 2024 eruption, 2023, a little later in the talk. Now, I'm talking about volcanoes, but I always start my talks reminding you of what our most important geologic hazards are here on the North Coast, namely earthquakes, and especially earthquakes followed by tsunamis. So please remember that when the ground starts shaking, you stay put. If you're physically able, please drop cover, get under a sturdy table or desk if nearby. If not, just stay where you are. People get injured because they try to move during and immediately after strong ground shaking. Know your tsunami zone. We have lots of resources to help you do that. Just go to the Redwood Coast RCTWG website and you can find maps, locate where you are. if you're in a tsunami zone and you feel earthquake shaking, that's your warning. Don't wait to hear from somebody else. Get inland or head to higher ground. And then it's really important to stay there. So, Iceland. I was there in July of 2023, and I had never been quite so far north before. So it's important to realize that Iceland is just on the edge of the Arctic Circle, which means in the summer, it stays light all the time, and in the winter, it's dark. Iceland covers about 0.02% of the world's surface, yet over 3% of the world's volcanoes. So we definitely have a bit of a disjunct there, tiny bit of surface area, and yet lots and lots of volcanoes. Turns out the US has more identified volcanoes than anywhere else in the world. Almost all of those are in Alaska's Aleutian Islands. We certainly have some in the Pacific Northwest, and one not too far away from us in Mount Lassen. So the permanent population of Iceland is just under 400,000. So, you know, we're talking about a pretty small place in terms of the number of people, 2/3 of whom live in the greater Reykjavik area. And Reykjavik is down here in the southwest corner. In contrast, the 2022 tourist population was 1.7 million. If you go to Iceland in the summer, you probably won't interact with a whole lot of native Icelanders, because pretty much all of the folks who work in the hotels and restaurants, etc., have come from all over Europe, and they work there in the summer. Iceland has essentially 0% per capita fossil fuel consumption. The only fossil fuel consumption is what they still use to drive gasoline cars. It's an extraordinary country in that they've been able to harness both geothermal energy and hydropower, more waterfalls than you can imagine. I won't talk about waterfalls today, but they got plenty of wind too, but they don't even need to try to get wind energy. They boast Europe's largest glacier. Iceland is considered a part of Europe. There are no mosquitoes on the island. There are midges. I can attest to that. No McDonald's, world's third lowest murder rate. Largest electricity per capita producer in the world. No indigenous populations. So unlike Greenland, where Inuit people have been living for thousands of years, nobody lived on Iceland before the Norse arrived in the 9th century. Never been invaded, although during World War II, when it looked like the Germans might have their eyes on Iceland, the British peacefully took over the country, and during the course of World War II, it was part of Great Britain. Arctic fox is the only native land animal. Okay, come on now. Why is this? All right, there we go. So I'm going to give you a little overview of human history in Iceland, but we'll mainly be focusing on geology. Why volcanism? What causes it? Mid-ocean ridges, and the origin of the Atlantic Ocean, hotspots, and more about volcanoes and glaciers. Then we'll get into the recent eruptions starting in 2021, still basically ongoing, and a little bit on other volcanic hazards. So Iceland was covered with ice in the last ice age. And really the land didn't begin to emerge until about 8,000 years ago. And with the exception of the Arctic fox and lots of seabirds, basically unpopulated until 870. It's a little over 500 miles from Scotland, 630 miles from Norway, and 680 miles from Ireland. And all of these countries contributed to the present makeup of the island. The settlement period is really quite short, about 60 years, 870 to 930. Most documents claim that 874 was the first permanent settlement. There were a number of brief explorations before that. But by 930, it's considered to be, quote, fully settled. In other words, all the farmland that you could possibly farm had been claimed by then. Real variation in terms of the number of people thought to have emigrated, somewhere between 4,000 and 24,000. Obviously, not all of them made it. And many of them, especially those that came at the end, like Eric the Red, the father of Leif Erikson, they came fairly late in the game when there wasn't very good land and quickly moved on to Greenland. And that's a whole nother story that we won't get into today. Estimated roughly 3,500 people lived in Iceland at the end of that settlement period. Now, when these folks arrived, about 40% of the land was covered with forests, birch forests. Needless to say, they very quickly cut down the trees, burned them, made ships, and today it's roughly 2% of the country, although there are some forest plantations being planted. It's real interesting to look at the genetic makeup of the Icelanders, both the early ones and the folks today. And by examining the DNA of the settlers, they're not all Norsemen. In fact, 57% Norse, about 43% Celtic, in particular Irish, and then also Scots and Brits. The story goes that the men who sailed and led the expeditions from Scandinavia were Norse, but the Norse women had no interest in getting into those boats and leaving home. And so the Norse would swing by Scotland or Ireland and pick up willing or unwilling women along the way. And in fact, a large percentage of the population, perhaps 30–40% in those settlement days, were slaves and called as such. It's interesting that the DNA of the present population is higher in Norse than it is in Celtic. And the matrilineal lines have far more Celtic than the patrilineal lines. And that's about it for talking about the peoples. It was not an easy life in Iceland in those early years, and winters today are still not particularly easy. This is a soil core, in other words, sinking a shaft down into the ground, pulling it up, and then looking at the layers. We do a lot of that in geology. So this is the top. This is about 1 meter, 3 feet long. And you can see all these different layers. And it turns out these light layers, for the most part, are ash deposits, the tephra, the ash from volcanic eruptions. And you can see there are a bunch of names here. This is the source. What's cool about volcanic ash is that it's like a fingerprint for a volcano. The chemistry of a particular eruption, even from the same volcano, will be distinct. And so folks that look at tephra, which is our name for the ash material, all the stuff that gets blasted into the air, they can distinguish very clearly specific eruptions. Can do the same thing in the Pacific Northwest. So the Mazama ash from what used to be Crater Lake is very distinct from Mount St. Helens ash, and the different Mount St. Helens eruptions will all have different chemistry. So you can see that Kafka and Hekla are quite common in here. I will murder some of these name pronunciations. So all of you people who speak Icelandic, apologies in advance. So in addition to just difficult weather conditions, hard for agriculture, about on average every 3 years they'd have to deal with an eruption. Now this is a core from southern Iceland. It's going to look different in different parts of the country. So in order to understand why Iceland is a volcanic place, you're going to have to bear with me and have a little bit of basics about Earth structure and volcanism. So if you imagine the Earth as a marble, it has a number of layers. We live on the tiny, tiny outer edge, the crust. So all the rocks you're familiar with, sandstones, granites, etc., they are basically trivial as far as the overall mass of the Earth is concerned. The largest area is what we call the mantle. And the mantle is made of rocky types of materials, but denser, heavier, more iron, magnesium, manganese than what we see with the rocks at the surface. But still definitely rocky and definitely solid. We know that because seismic waves can easily get through it. The only part of the Earth that's actually molten is the outer core, and it's basically an iron nickel alloy, and we think it's fluid because seismic S waves can't travel through it. And then the inner core is the solidified, same iron stuff, but the pressure is sufficient that it's actually crystallized. Now over on this side is a graph showing depth. So there's the center of the Earth, about 6,400 kilometers, 3,500 miles or so. And then here we have temperature in degrees Kelvin. The orange here is the mantle. Then we get to the molten outer core, inner core. We're not really going to worry about the core in this talk. This black line is an estimate of the temperatures in the Earth. We call it the geotherm. So yeah, it gets a lot hotter as you go deep. And the hottest part of the Earth is down here in the center. The red line is the melting temperature of the rock. So you'll notice that throughout the mantle, the temperatures are below the melting temperature. That means the mantle's solid. Unlike some shows and some books I've seen, we're not floating on a sea of lava. We call it magma when it's deep down in the Earth. So the mantle is solid. Seismic waves travel through it. When we get to the core, then you see the actual temperature is below the melting temperature. And then when we get into the solid inner core, we're back into an area where we're solid again. Now, note that up here, they're looking pretty close together. And that's going to be really important, both in terms of generating what's going to end up as lava at the Earth's surface, and also in terms of moving the plates around. I'm going to assume that most of you have a little bit of understanding of the mobile surface of the Earth, where the outer 50, 60 miles is stiff and is able to sort of move relative to the lower part. And it's this thing that we call the asthenosphere, which is really, really close to the melting temperature. But it's not molten. We might have 5% actual melted rock there, not very much. This is important in allowing our plates to move. It's also going to be really important in helping us to generate magma. The Earth is not uniform, and there are places where the lithosphere is thinner. There are places where the temperature is warmer. And depth is really a proxy for pressure. The more pressure you have, the harder it is to melt things. But if you're kind of near the surface and in this zone and you have less pressure, then suddenly you can melt more rock. So the molten rock is what we call magma. Molten rock makes it to the surface in a number of places in the world, but it's really fairly restricted. So this is a USGS map that shows map volcanoes, these red dots. Here's all of those Aleutian volcanoes. There's always a couple of them erupting at any time. Fortunately, it isn't a problem unless you're in an airplane that happens to be flying over one of these eruptions. That's one of the reasons why the US puts a lot of money into monitoring volcanism all over the world. So Russia doesn't do much about monitoring its volcanoes, but the US monitors these because we really don't want to fly into an ash cloud. So you can see that they're restricted to certain places, generally on what we call plate boundaries, particularly subduction zones. That's our kind of Pacific Northwest volcanoes like Lassen. But there are a couple of places here in the middle of plates, way far away from these boundaries. We have Hawaii. We have a number of this map doesn't show all of them down here in the southwestern, well, certainly in the southwestern Pacific, but also in the southern Pacific. But all of these black lines going through the middle of the oceans are also places where we have volcanic activity. We call those ridges or rifts. So subduction zones, ridges, rifts, and hotspots are the places where conditions are such that we're able to melt enough rock and get it up to the surface. So we see very distinctly different types of volcanic activity depending on where we are. So here in the Pacific Northwest, our volcanism on land is related to subduction zones. And this is where we get the classic composite or stratovolcano. What really defines a Mount St. Helens or a Mount Mazama is that sometimes they produce lava flows and sometimes they explode spectacularly, producing a lot of tephra, ash, and pumice. So Mount St. Helens, Vesuvius. Here we are looking at a portion of the seafloor along the mid-Atlantic ridge, and you can see this little fissure right here. This is typical of the kind of eruptions that we get along ridges. In fact, the most volcanically active part of our area is only about 150 miles offshore along the Gorda Ridge. And the Gorda Ridge experiences little eruptions like this every couple of years. Most of them we don't even know about unless we have some kind of monitoring to see them. They tend to be very short-lived, only a couple of weeks, and they don't cause any problems for us. They essentially never build up enough land to rise the seafloor above the ocean level. And finally, we have hotspots. And a hotspot is very different if it's beneath a continent or if it's beneath the ocean. Think Hawaii, that's your typical ocean hotspot where you get lots and lots of really fluid basalt flows. Under a continent, it's very different. So Yellowstone is considered a hotspot and arguably the potentially most explosive center on Earth. So a little bit about what comes out of a volcano and volcanic hazards. This is really a model over here of what we would call a composite volcano, the kind of thing you know, a Mount St. Helens volcano. And we can have an eruption cloud, which is made up of particles, sometimes bits of old rock, sometimes bits of new rock, the magma that's cooled up in the air, lots of gas and steam in it. Then we can have lava flows, beautiful Pahoehoe flow here from Hawaii. Here we see the great big, what we call Plinian column, named after Pliny the Elder, who described and died in the 79 AD eruption of Vesuvius. But not all of the hazards associated with volcanoes are caused by the magma moving up. All we have to do is melt some snow or glaciers and we can get these catastrophic lahars or floods, muddy floods, debris flow floods that can be quite deadly. We don't have anything like magnitude, earthquake magnitude to describe volcanic eruptions, but we do have a qualitative terminology called volcanic explosivity index, or VEI. And it ranges basically from 0, which means we don't have anything up in the air, to a category 8, which we've never experienced. So, I mean, it was roughly 600,000 years ago, but we don't have any photographs, sorry. But you can kind of see as we go up in number, this is Pinatubo, the most recent VEI 6 eruption, as we get more and more effusive, explosive as we go up in number. Typically, the low numbers, the 0s and the 1s, erupt very frequently. And the real big ones, fortunately for us, may go tens or hundreds of thousands of years in between. So now let me talk a little bit about Iceland. And where does it fit? It actually doesn't fit into any of those nice categories because it's partly a ridge. And here we're looking at a model of the opening of the Atlantic. You can see how the Atlantic is getting bigger and bigger. 100 million years ago, right about here is where we have Iceland today. So Iceland sits and straddles the mid-Atlantic ridge. But Iceland is also a hotspot. So a hotspot is a place, not a swinging nightclub, but geologically, it's an exciting place where we think heat is really concentrated in kind of a plume that may originate way down here on the core mantle boundary. Now, this isn't fluid. This is just hotter than the solid rock around it. So it's moving very slowly, about the rate at which your fingernails grow. But it's very concentrated and it's essentially fixed in space relative to some kind of perturbation down here on the outer core. So you can think of it as like the burner on a stove, and you've left something on top of it. And if you slide, oh, let's say it's a big cutting board, and you slide that cutting board on top of the stove, you're going to end up successively burning spots on your cutting board, if it doesn't set on fire, that leaves the scar a trace of where that plate was before. And the classic example of these hotspot tracks is in the Pacific, where we actually have a number of these islands that have left these scars of where the overlying plate was before. So here we're looking at the Pacific and the Hawaiian Island, Explorer Islands. And right here is where the big island is today. And it's actually not erupting at the moment, but it'll probably be erupting again in the next few months. So then we get progressively older. Kauai last erupted about 4.7 million years ago. Midway, just under 30 million years ago. And then we start seeing these chains, these very small islands in the Explorer chain. The oldest rock here is maybe 68 million years. So this tracks the motion of the Pacific plate over the hotspot. Something very interesting happened 42 million years ago, and that's the subject of a different talk. And when you're looking at these tracks, you can figure out how the plate is moving. In this case, it's moving towards the older ages. So here's the situation in Iceland. Here we have the Mid-Atlantic Ridge. And here we have the track of what we call the Iceland hotspot. 80 million years ago, it was roughly in this location. In other words, Greenland was to the south of it. And Greenland proceeded to move over, leaving actually, this is a thermal signature. We can still see the thermal signature millions of years later as Greenland moved over that hotspot. And today we have a truly unique spot on the planet where the ridge and the hotspot basically coincide. At first glance, it may not look that complicated. So here we have the Mid-Atlantic Ridge slicing right through Iceland. But it's not clean or simple. And when you start digging into it, you can see it gets more complex. Here we're looking, this would be the Mid-Atlantic Ridge. We call the part to the south the Reykjanes Ridge. We call the part to the north the Kolbeinsey Ridge. This GF, which is the Guyuk Ridge, 30 million years ago, these two sides were together. That's how much they've moved in 30 million years. Oh, people have spent a lot of time trying to reconstruct Iceland's history, and I'm going to give you a simplified version. So about 60 million years before present, that's the MYBP, the northern mid-Atlantic ridge began to open, and that lays the foundation of Iceland. 25 million years ago, we start, the hotspot is close enough to the ridge that we get excessive production of lava. I mean, that's what makes an island in the ocean. You've got to keep pumping lava onto that surface until it finally gets above sea level. Well, it took almost 10 million years of pumping out lava on the seafloor for Iceland to finally get its nose above the water. So here's roughly 15 million years ago, just tiny, tiny land. And we successively grow, and Iceland continues to grow today, partly because it's spreading. It grows thicker and wider every year, again, roughly at the rate of which what your fingernails grow. And it keeps becoming more massive. It's in the last 2.5 million years, we've had successive ice ages, and Iceland completely covered, and the land begins to reemerge, especially the land around here, Reykjavik and the Reykjanes Peninsula, that I'll be talking more about later on. It basically reaches the surface about 8,000 years, or it's exposed to the surface. Ice has melted roughly 8,000 years ago. So it is a really complex, rapidly evolving island. Again, simplified, here we have the Reykjanes Ridge, and here we have the Kolbeinsson Ridge, but we actually have a kind of a bifurcation. We have these two separate pieces of the Mid-Atlantic Ridge. This is the famous spot. It's a photo I took last summer, standing right about here, looking south. And you'll see all the signs saying, oh, this is the North American plate and the Eurasian plate. It actually isn't the Eurasian plate. You'd have to go another 20 miles to clearly get to the Eurasian plate. There's this little complex microplate in between, but it's still a way cool place to see, and it's wonderful to hike along here and sort of imagine that the two sides are moving away from you at a couple of inches per year. There are 43 named volcanic centers in Icelandic. There are 35 volcanoes that have clearly erupted in the last 10,000 years. We call that the Holocene. And 54 specific eruptions in NOAA's National Center for Environmental Information volcano catalog. So these red circles are some of the named volcanic systems. There's Eyjafjallajökull, which we'll briefly get back to in a bit. And you can kind of see that there are a lot in this band, and then there are some over here. And there's really not much down here on the Reykjanes Ridge. And here are a couple of examples. Hekla, one of the most active. There's Eyjafjallajökull, caused a lot of disruption to people's lives in 2010. And this is Eldfell. If you ever go to Iceland, be sure to go to the Westman Islands, because it's a fabulous place to look at. And the eruption of Eldfell in 1973. Not surprisingly, Iceland is made up of volcanic rocks. There are different kinds of volcanic rocks. Basalt is by far and away the most common. It's what the seafloor is made up of, all created along those ridges. It's what Hawaii is made up of, and we have a share of basalt mixed in with other rocks in the Cascade volcanoes. We call these basic rocks. They're heavier, they have more iron and manganese and less silica in them than what we call intermediate rocks. Cascades have a lot of andesite. They often are a little speckled. You'll see the black rock with little white crystal flakes in them. And then the more silicic, the rhyolites, they're very light colored. So these are some pictures I took in Iceland. Here you can see typical columnar basalt, really the most common rock in Iceland. Then you can see these sort of intermediate rocks. This one has got chunks of things in it. And here are the light colored rhyolites. And this is a huge surprise to me because when I went to Iceland, I fully thought I understood hotspots. I understood ridges. So of course, Iceland is going to be all basalt because ridges produce basalt and hotspots beneath the ocean produce basalts. Yet here is Iceland with a surprising percent of non-basaltic rocks. Why? I really scratched my head on that. And it's due to the fact that Iceland has the world's thickest oceanic crust. The oceanic crust in most parts of the world is really thin, only a few miles thick. But this combination of ridge and hotspot have been pumping and pumping and pumping magma upwards that it's gotten so thick that it behaves more like what we see with volcanism on land in subduction zones, in particular, where the heated material doesn't just go boom from down here at the bottom up to the top. It kind of works its way up slowly and has resting spots in between. And in these sort of resting spots, you start to get some crystallization. And it turns out the more mafic or basic or iron bearing crystals, they crystallize out first. And so we call this differentiation. We're losing the stuff that would become basalt, and we're getting a more silicic magma as we move upwards. And so Iceland is not a continent, but it's behaving in some ways more like a continental volcanic system. This Dept, the deepest parts, it's about 25 miles thick, determined from seismic lines, and those are the seismic lines. Now, it turns out the thickest part of the crust, where we're most likely to get this differentiation and produce these more explosive kinds of magmas, are in the same part of the island where it's the highest and where we have glaciers. So this is actually an outline of the largest glacier in Europe, Vatnajökull. So that's going to play into the story with hazards as well. Well, let's look at eruptions in the relatively recent past. So here's a map I've compiled of eruptions between 1900 and 2015. There have been 6 eruptions of Hekla. It's been the westernmost type of eruption. But a whole bunch down here, this is Surtsey, the island that grew out of the ocean. I think it was in the 1960s. Yeah, 63 through 67. And you can see there have been a number extending in this eastern belt. Nothing over here. Now, Iceland expends quite a bit of resources in studying their volcanoes. So when things are changing, they can tell. So remote sensing, seismic lines. Turns out when you push magma up to the surface, it's going to make earthquakes. When you push magma up to the surface, it's going to bulge. It's going to cause deformation. You can measure all kinds of geophysical properties, electrical, magnetic. When magma moves closer to the surface, there's less pressure on it, and so gas starts coming out of solution, and you can measure the gas. So all of these things Iceland does in a very detailed, sophisticated way. So at the end of 2019, earthquakes started being detected in much higher numbers than had been seen before in the West, in the Reykjanes Peninsula area. It started with a swarm, and over the next 19 or so months, 50,000 earthquakes were detected, including several in the magnitude 5 range, which is unusual for Iceland. The Iceland Meteorological Agency, that we call Iceland Met, put out alerts and stating that an eruption was likely in the next days or weeks in February, and in March, that was the beginning of the first eruption in about 800 years in that area. And that eruption continued off and on for many months. So we're going to look at the activity here on the Reykjanes Peninsula. And here's Reykjavik. And if you ever go to Iceland, you'll land right here in Keflavik. And here's the town of Grindavik, where we had lunch our very first day in Iceland. And here is the location of the famous Blue Lagoon, one of the most famous tourist spots in Iceland. So this eruption was centered, and a dot doesn't really express it. It lasted from March 19th to September 18th of 2021. It's actually the longest documented eruption in the 21st century in Iceland. It caused no damage and no injuries and produced quite a bit of tourist revenue. To get a sense of what that eruption might mean, it's always best to go to the past. So let's look at all of Iceland is volcanic. So there were definitely eruptions there in the past. Well, the only historic eruptions in this area that occurred since settlement occurred in the Middle Ages between 940 and 1340. They are called the Crucifix and Reykjavik fires. That's sort of the name of a eruptive sequence. And the sequence kind of began in this area and then moved down to Crucifix, which I also visited. And then it ended up sort of in the Svartsengi area, which is where the power plant is today. So most of these eruptions were similar to what we've seen more recently, relatively modest, non-destructive, and it ended very suddenly in 1240. But not all of them were so benign. In 1226, there was a very explosive eruption. We don't know where it was centered. Some people guess that it may have been down here. And it was very explosive, not because its composition was different, but because it was centered beneath the seafloor And when even basaltic magma, which is generally not explosive, but if it comes into contact with seawater, it can be spectacularly explosive. If you might remember the 2022 Tonga eruption, the highest explosion we've ever recorded. That was basaltic magma, but it came into contact with seawater. So the 2026 eruption produced an enormous amount of ash called the darkness during the daytime period. And the following winter was described the sand winter because ash continued to rain out of the atmosphere. It left the largest aerial tephra deposit in historic times in Iceland. And unfortunately, it killed crops, it killed livestock, and there was widespread famine. So keeping that in mind, very early on after the first eruption in 2021, geologists and volcanologists started saying, well, are we in for a new Reykjavik or Reykjanes fire period? Well, it took about a year later, and there was another very similar eruption in August of 2022. It was very similar to the one that had happened the previous year. It also produced no damage. And then a year later, less than a year later, this was my eruption because we got on the airplane to fly to Iceland on July 10th, right when this eruption started. And you can see these are all kind of in a line. And they were all very similar. And this is what greeted us as we were picking up our rental car at the airport, was this lovely little steam plume. Was pretty much only steam, a little bit of particulate in it. And the whole time we were there, basically, that eruption was ongoing. You might think, okay, we would expect a year later something similar. Well, Mother Nature always likes to try something new. Here's where these three eruptions were: 2021, 2022, 2023. And we suddenly have a sequence of at least, I may have left one of these out. We have 6 more eruptions in between December 2023 and only a few weeks ago. And these eruptions are all located just north of Grindavik to the west. The Tsunami eruptions. These eruptions have not been nearly as benign, for the simple reason that they are closer to population centers. They all have looked very similar along a long rift like this. They typically are very active in the first couple of days and then slow down quite quickly and have been done pretty much over in about a week or two. They've produced much more lava than the earlier eruptions that were further to the east. And in populated areas like Grindavik, they've caused a lot of damage. Grindavik is a lovely coastal town, population around 2,000. And the magma rising beneath has caused profound surface deformation. The only death so far in all of these eruptions was a construction construction worker who was filling in one of these cracks weeks afterwards and unfortunately fell into the crack, and his body was never retrieved. So real hazards in working in a situation like this. The other problem is that the eruptive site is very close to the Svartsengi power plant, which produces the power for essentially the whole Reykjanes Peninsula area, the Keflavik airport, all of the communities near there. Reykjavik gets power from another power station. And there was one of these lava flows actually cut the hot water line running to Keflavik and all of those communities. And for over a week, they were without hot water, which you don't have any other source of hot water in Iceland. It all comes from these geothermal plants. One of the things that really impressed me about the way the Icelanders handled this situation, as I said, Icelandic Met is monitoring, and they can tell by the earthquake pattern and the ground surface deformation, typically within a day or two, that an eruption is imminent. And they can give these communities, about a 6-8 hour window heads up saying, you got to get out. Well, Grindavik has repeatedly evacuated, gone back, evacuated, gone back. They can evacuate their entire town in less than 20 minutes. Now, over here, not only is the power plant, you can see here is the Blue Lagoon with all of these people enjoying the naturally warm waters. And Blue Lagoon has also repeatedly closed, evacuated, reopened. It's open again right now. It's been absolutely fascinating to watch how Iceland has dealt with the volcanic hazards. So as soon as that sort of earthquake activity began in late 2019, and indications were that, yes, we're likely to have an eruption, they had to wait a little longer until they could sort of define the area of uplift where the eruption was likely to be. They built these series of big berms to deflect the lava flows. Now you can see over here, here's what happened to the roads. This is the road we drove to get to Grindavik. Obviously you're dealing with an awful lot of material, and when the volume is sufficient enough, you're not going to be able to deflect it. So far, they've been able to keep the power plant. The power plant operates completely remotely. Nobody is on site there, but they've been able to keep it going. And with each successive eruption that kind of covers where the hot water pipeline goes, they just pack a whole bunch of more gravel on top of it, lay another path, and put the hot pipeline on it again. So far, it's working, but the future is very unclear. So this is the most recent assessment that Icelandic Met put out on September 24th. And this was looking at earthquake activity in September. And you can see how this is the lava flows that have basically been produced in the eruptions in 2023 and 2024. From the earthquake patterns, it's a suggestion that maybe the next center will move a little to the east. they draw up very detailed hazard maps, and then obviously as the situation changes, they may order evacuations and so forth. But the long-term prognosis is very unclear. So far, they've been able to handle these events quite well. But if a future eruption occurs offshore, here's Grindavik right here, we could end up with something perhaps more like what happened in 1226, where you get a massive steam eruption, or perhaps another system further to the west or closer to Reykjavik could occur. So a lot of uncertainty as to what is going to happen next. The other thing I wanted to mention is that the Reykjanes Peninsula are not the only volcanoes that Iceland has to deal with. So those much larger composite kind of volcanoes in the eastern part of the country are certainly going to erupt again. And with the potential of a huge ash, this is the ash cloud that covered much of Europe in the 2010. We don't even see Iceland on this. You know, Iceland's way off to the left. Here's Denmark, Germany, the Netherlands. You can see this is why air travel was completely shut down for about a week. That could certainly happen again, or certainly will happen again at some point when we get a more explosive type of eruption from one of these larger volcanic centers. And I did promise a friend I would mention Jökulárfoss, an Icelandic word that means basically glacial outburst. So we saw earlier on that some of these largest volcanic centers are beneath glaciers. So when a volcano erupts beneath a glacier, it's going to melt a lot of that ice. And some of the world's largest floods are what we call glacial outburst floods that can sweep away everything downstream. And so the entire country of Iceland has been mapped. Everyone who lives in the area of a potential Jökulárfoss event supposedly is tied into communication network so that they are able to evacuate. So I'm going to wrap up with a message to you to think like Icelanders, recognize your threats, embrace them. I mean, Iceland makes a lot of tourist dollars over their volcanic hazards. Plan to be safe, come up with innovative solutions, and please be prepared to evacuate at a moment's notice if you need to. Our biggest concerns are earthquakes and floods, and we can certainly have a similar scale of disruption here as to what Iceland has experienced in the past. Actually, I forgot to correct this. Shakeout is October 17th. It's always the third Thursday in October. Time to practice a drop, cover, and hold on drill. And that's one of the best ways to both have fun. It's interesting to take photos of yourself under a table and develop the muscle memory to do the right thing when the ground starts shaking. Lots of folks I work with in emergency management and emergency planning on the North Coast. Here's just a few of them. And as I said, Thursday, October 17th, please follow us on Facebook, visit the Redwood Coast Tsunami Work Group site, and I'd be happy to answer any questions that are in the chat or any questions that you might have. And with that, I'll stop my screen share.
I have one.
Great.
It's about hotspots. And I remember a New York Times article earlier this year reporting on a Nature article that talked about Theia, the planet that slammed into Earth 4 billion years ago. And the point of the article seemed to be that from that collision, there was a mountain of apparently magma or something else resting on the core of the Earth that is the source of plumes. Do you know about that? What do you think of it?
I actually have heard a little bit. It's not a story that I've followed closely, and I don't think that it's been generally, well, it's an interesting idea. How do you get irregularities on the core mantle boundary? And, it's a couple of thousand miles down below us, and we definitely cannot directly sample it. So our only source of information is seismic waves, and seismic waves don't provide the scale of detail. It's a question of what, clearly it's an issue that affects the entire Earth. It's not like hotspots are all clustered in one part of the Earth. We see them really distributed widely over the Earth. And they also appear to have a distinct lifetime. So the Icelandic hotspot is arguably about 80 million years old. The Hawaiian hotspot may be somewhat similar. So we really don't have the record of a hotspot continuing for billions of years. Now, there are a lot of other Earth processes that might erase that evidence, but at this point, I'd call that a kind of a long shot idea. But it's an interesting idea. I mean, that collision did produce the moon, so we know that it produced something. But exactly what happened, it essentially caused much of the Earth to become molten. And so the Earth really rearranged itself following that event. So did it exert some kind of influence? I don't know.
I understand that computer modeling was a big part of this research. And do you know how much of our iron and nickel in the core came from that collision?
Probably not. It was probably already here. And so, you basically got, in the early stages of planetary formation, there's a lot of heat, because just when things come together gravitationally, we call it gravitational self-heating, they get hot. Plus, you've got a lot more radioactive elements at that time that are also producing heat. So, and in that essentially hot phase, you're going to get a lot of differentiation. So we didn't really need something else to bring in the iron and nickel. It was already part of the mix.
All right, thank you.
I have a question. The Atlantic Ridge is an example of where the Earth is growing, and there are other ridges where it's growing. Is that not correct? Where more
so where it's opening, we won't say
it's opening up.
Oceans are getting bigger. And it was kind of interesting at some of the early days of seafloor spreading ideas, early 20th century. Alfred Wegener is the person who, he wasn't the first person to talk about, I mean, back in the 16th century, We had, when the first sort of maps of the Atlantic were, I mean, Bacon looked at the maps and said, oh, I can see how these, how South America and Africa fit together. But it was Wegener in the early 20th century that really wrote a lot about this idea of seafloor spreading. And so there was this idea that some people said, oh, the Earth is somehow expanding, because obviously if it's like Iceland is getting bigger by a couple of inches every year, then if everything into it, and we have ridges in the Indian Ocean and ridges offshore of Humboldt County. But that was pretty much scotched when we got a better understanding of subduction zones, because in some places we're expanding, in other places we're consuming. And now we have so much satellite data in terms of the shape of the Earth that the Earth's size is not changing. Its shape, there are some changes in shape going on all the time, but the size is not. So the Mid-Atlantic Ridge is a place where we're creating new ocean crust, and it's being consumed on the other side of the world in the Pacific, where we have subduction zones. So the Pacific is getting smaller. The Atlantic is currently getting larger.
Do these ridges, and does this spread occur as a result in part of the gravitation of the bulges that occur as a result of the gravitational effects of the sun and the moon?
No, it's really it's being driven by the temperatures within the Earth. And so it's the temperature, the Earth is cooling down. Eventually, we won't have any of this going on because the Earth will become cold. All the radioactivity will be done. All of that initial heat will have dissipated. But right now, the interior of the Earth is hotter than the surface. And so the heat comes up. And the most efficient way that the Earth has developed to get rid of heat is by concentrating it in certain areas, these sort of plumes, the heat coming up. And then when you have a big, thick continent, think Africa today, heat is not nearly as efficient at getting through continental crust as it is getting through the ocean. So it starts welling up, and it bulges Africa, and then it starts splitting it. And we're seeing that today in Africa's Rift Valley. So a new ocean is being born today in the African continent. And 30 million years from now, there'll be a clear inland sea that will separate East Africa from West Africa. And then another 30 million years from then, it'll be a real ocean. And once you start spreading, it's hot. The rock, as it's further away, gets colder and colder. And eventually, it becomes so cold that relative to the continent next to it, it founders. It starts dropping down back into the deeper mantle. And that's when a subduction zone is born. We've never really seen a subduction zone being born. So that's still kind of, theoretical. But my guess is in about 15 million years, we'll start getting subduction zones at the western edge of the Atlantic, and Washington, D.C. will start getting earthquakes.
We won't be around to notice. Didn't we used to have a divide or the potential of a divide in the middle of the United States? Or is that just something I read somewhere?
No, I mean the North American plate, which is all of the US, all of Canada, into Mexico, we think of it as kind of one piece that extends from the middle of the Atlantic all the way to our edge. We're at the edge. Now, obviously, it's not uniform. And there's differences in thickness of the crust. There's differences in temperature. And it also bears the scars of ancient geologic events. So we know that there are very large earthquakes can occur in the Midwest. In 1811 and 1812, there were a series of very big earthquakes. We call them the New Madrid earthquakes in southeastern Missouri and in Arkansas. They were huge, may have been magnitude 8, close to magnitude 8. And that's nowhere near a plate boundary. And so it's always been kind of a question what caused those earthquakes. The explanation that I like is there's sort of two components. One is changes in stress along a lot of northern North America due to the recession of the ice caps. I mean, the ground is popping up and it doesn't pop up uniformly. So there are stresses due to that. And there may also be scars due to the original opening of the Atlantic way back around 200, 250 million years ago. If you look at what's happening today in Africa, we have the Rift Valley, but we also have a couple of other rifts that are sort of parallel. And I think of them as kind of stretch marks. You know, it's not like eventually one is going to win. And those other scars of that stretching are going to be embedded in the African continent for a really long time. As I say, Earth materials have a long memory. And so one of the arguments for those potential for really big earthquakes, not just in New Madrid, there was a very big earthquake in South Carolina. I think it was in the 1860s. And so those, we can have a big earthquake anywhere, just not nearly as frequent as we do in a tectonically active place like here.
Yeah. Are there any other questions?
One of the cool things about Iceland that has to do with global warming is that they are actually rising relative to sea level rather than falling. So what's happened, I mean, Iceland was completely weighed down, covered in ice 8,000 years ago, 10,000 years ago. Now, only about 11% of Iceland is still covered with very small glacial ice caps that are melting like crazy. And as that weight goes away, Iceland pops up. And so Iceland actually is rising. They have a falling sea level issue, not a rising sea level issue. So there are all these really interesting things about the Earth system that don't have one simple answer.
Are there any other questions from anybody?
Yeah, well, apparently we're sinking at the rate that Iceland is rising. How could you compare those rates?
Well, and it's not just us, because Crescent City is rising.
Yeah.
Humboldt Bay is sinking. Crescent City is rising relative to sea level. And that's because the tectonic input, if Earth forces are pushing you up faster than sea level is rising, what's going to happen is that your relative sea level will fall. And that's one of the sort of interesting enigmas on the West Coast is both Bandon and I think it's Bandon. It's the station that's just north of Crescent City. Those two stations show relative sea level drop. In other words, the land is going up faster. Whereas Humboldt Bay, we see very rapid sea level subsidence, or the sea level is rising.
Mm.
And we haven't come up with the perfect solution to explanation for why that is happening, but we know that the tectonics at the southern end of the subduction belt are extremely complicated.
Hmm. You think we'll bounce back in the big one?
Well, what
think we'll
happens, we
move it.
know what happens in big earthquakes, that you get a sudden change in elevation in the minute of the event, and then decades and centuries, there's a slow rebound. I believe there's still rebound being measured in Alaska after 64. I'm not absolutely sure of that, but I believe there's still some. It's much slower, but
Hmm.
yeah, it's complicated.
Any other questions? No? Well, if not, I'm going to say thank you to Lori once again. And you can look forward to another talk in the spring, because I asked her and she said yes, she would. So we're going to have another in the spring.
March 24th will be the 1954 magnitude 6.5 Blue Lake earthquake enigma.
Oh, that's,
God.
I'll sign up for that.
That should be fun. And I want to remind you all that next Monday, we're going to be talking about with the Week of Women Voters is going to be talking about the pros and cons of the statewide ballot measures in November. So don't miss it if you haven't. I mean, I haven't gotten my ballot yet, but have any of you? No?
It's been mailed.
Oh, well,
You haven't
it may
got,
get
you'll
here
get it like
next week.
tomorrow.